you are not aware, Dr. Dumbia also has a course in Coursera on data science. You want to check that out, you will also benefit from it. So without any further delay, I will hand over to Dr. Musa. So Musa, it's all yours.
Okay, good morning, everyone. Welcome to our classification models, day 2. So today I'm planning to cover support vector machine and K nearest neighborhood. Before that, I want to refresh our memory about this concept because we'll be using the precision, accuracy, and F1 score to determine whether or not our model is performing well. All right, so just to refresh, the accuracy we discussed yesterday, that is the total, right, instance that we classify correctly divided by the total number of instances, right? So, and the precision is a total true positive divided by the sum of true positive plus false negative, false positive, right? That's a precision. So basically is the positive that we classify correctly divided by the actual total number of positive cases. And a recall is a true positive divided by true positive plus false negative. And F1 score depend on the precisions and the recall. So it's 2 times the precision times the recall divided by the recall plus the precisions. Right. So we use F1 score, right? Usually people prefer that because it kind of avoid the concept of true and false, a negative or positive one, right? Especially if your data set is a large number of actual negative cases. So today I want to start with nearest neighborhood, K nearest neighborhood, right? Classifications, KNN. Right, so imagine we have a data set about dogs and horses. Let's say this is a fake data, by the way, right? The blue one are dogs, and then the red one are horses. And then on the x-axis, we have their weight. On the y-axis, we have their height. Right, obviously, if you look at it, some of the blue dots, which represent dogs, got like 500 pounds. So it's fake, it's just for simulation. So with this data set, we want to predict if we are given, oh, can you see? If you are given, can you see? Can you see the PowerPoint still?
Yes.
Okay. So if you are given an animal with only the weights and the height, we want to be able to classify whether the animal is a horse or a dog, right? And KNN is, a type of classification model that can now help us classify the animal, right? So, for example, the green dots, we want to figure it out whether or not it is a horse or dog, but knowing the height, right, and the weight, it is more likely to be among the horse. So we'll classify this. But look at this green dot here, right, is almost at the boundary, but it is very close to the dog class, right? So based on the number of neighborhood that we choose, K is a value of clustering that we choose. So based on that, we'll be able to classify the green dots here as to dogs or horses. Right. So this technique is very simple, K-nearest neighborhood. What it does, it will store all the data in the memory, right? So that once a new, data set comes in, based on what he has in the memory, and then he would classify that using the distance, Euclidean distance. When I say distance, in this case, Euclidean distance, for example, right? So the closest neighborhood, you will be part of that class, right? So, like I say, it will store all the data. That's why this KNN will not do a better job if you have a data set that is more than 100K. With huge data set, do not use this technique, right? My screen is, am I in the presentation mode? Are you seeing the presentation mode? Okay, so let me try again. So KNN, one of the cons of KNN is that they don't perform well with a big data set, right? So because they have to, let's say you have millions of rows, they store all of those rows in the memory, and a new data set come in, so it will be computing the distance from that point to one of the other's data point. So pretty much 1 million calculations before you return the the results. Right. So pros and cons, right, is very simple. Like that's a pros advantage. The training is just trivial. It just kept everything in the memory, right? And then one of the advantage, another advantage is that KNN can work with any number of classes. It's easy to add more data set in it, and then fewer parameters. So those parameters are K, that determine the number of neighborhood. And then the distance, the metric distance, those are the two parameters for the model, right? Disadvantage, right? High prediction cost, right? It has high prediction cost, worse on large data set. Sometimes it takes forever before it returns a result to you, right? It's not good with high dimensional data set also. Right, it doesn't do good job with a categorical feature either. So now we know a little bit about K nearest neighborhoods. Let's work on some fake data sets using Python. Let me see some messages here. Okay, so this fake data, we want to use KNN. This fake data, it could be, if you get a job, for example, or sometimes company will give you a data set with little information about it. The columns names will be like A, B, C, D. So it's like a synthetic data. They have the consumer data set, but they will change the name of the columns, and then even change the value of the columns, and or scale it, give it to you, and then they ask you to just do some more data science, some machine learning, working on it, and then provide them with some results. They don't tell you what to do; they just give you a data set. So this is those kind of data set here, right? I'm gonna import pandas, numpys to work with a data set. I share that data set with Nana also, if you wanna reproduce. If you want it right now, I think I can also put in the chat. So first, I wanna import the library. Import pandas as PD. Import numpys as NP. I will import matplotlib that pyplot as PLT in case, and then I want matplotlib inline here, matplotlib inline, right? So I have this, Now I'm gonna get the data set that I already have it in this folder, and then I give a name of the data set to be classified data. Because you look at the column, it doesn't tell you anything, you know, it's hard to make sense of it. So df, I'll call that df is equal period read underscore CSV. So it's a CSV file, and then the name is just classified data. And then index called 0 for one. Okay, so now look at the head of the data frame. Okay, so that's fine. We have these data. So you see the column here, the name of the column doesn't tell much. This out of my way. And then this is our targets here, the last column, 0, 1, 0, 1, 0, 1. Right. Okay, so now, unlike decision trees and random forests and logistic model, this KNN and super vector machine, they need to have their data set normalized or scaled, you know, some standard, standardizing method, right? They need that in order for them to perform well. So we're gonna standardize our data set, right? So the X will be everything, our feature will be everything except the target. And then the Y will be the target only, right? So for us to scale that, we need to import the library. So we're gonna say from sklearn, the pre-processing, thing we're completing. We want to import standard scalar, capital S standard scalar. All right, got a message. Yeah, I think can I send it? Let me see if I can even put it in the chat right now. If I can, is that possible? Yeah, okay. I think I can. I think my computer. Yeah, okay. I want to put in the chat right now. VADSTI. Classify data. Classify. Okay. It's in the chat now for everybody. Right. Let me know if you don't see it. I just put it in the chat. Okay, so now I'm gonna instantiate this standard scalar. So I will just say scalar. My scalar is equal to that standard scalar. Right. And then I wanna feed that scalar, right? That fit. So we're gonna fit to our data everything except the target. So our df that drop targets, we're gonna drop the target here. Target class. Right, and then x is equal to 1. Did you get it, everybody? Did you get that data set? So that's our scalar. Now we want to our scalar is we feed it to our data, everything that now we want to scale feature. Scale feature is our scalar, right? We're gonna use that scale feature. The feature will be everything, every column except scale features will be equal to our scalar here that transform. We're transforming here our F. Yes.
Public tickets down.
Okay, I guess that's not me. Right. So we are transforming now. So target class. Right. Hopefully I don't have an extra space here. Axis equal 1. Right. And that's our feature, the scale feature does that. Now we can look at the head, right? DF feature will be equal to that. So DF feature, we're gonna DF underscore feature. So DF fit or fit FET will be equal to this. We're gonna just transform it to a banner data frame, period dots data frame. Right. And then we're gonna introduce our scale feature in there, scale feature, all of those columns will be there. And then the columns name will be equal to our data frame. Our data frame, everything from here, this is index 0, 1, 2, 3, up to here, up to this, right? So one way to do that is to say, we want every columns up to here. So you can use that by dropping, or you can say is equal to df, right? Our data frame dot columns. Right. In fact, let me run data from that column here, what it look like if you do df dot columns. It will return the name of all the columns, right? So it's a list. So in this list, we want to grab from here up to here. We want to grab all of these will be our column names. So target class will not be part of it. So slicing, list slicing. So that means we want all the rows and then all the column to the last one. That's how you do it. And then we can look at the head of this DF fit feature, that head. Okay, too many errors. Columns is equal df dot columns -1. Too many indexes. So I'll just do this. How about this? Let me just copy this. Put it this way, the hard way. So now I'll just say new calls or call name equal this. So I'll just take this part. So this is one way to do it. And then I would say here my column names is just equal to new calls Hall name, hall underscore name. So this is one way to do it too. Now, no problem. See here, okay. Yeah, so that's one way to do it. I'm trying to do slicing, is complain about some index. So now you look at the head, every number is between -1 and I would say between -2 and 2. Right, everything should be between -2 and 2. So now let's split it. Let's split our data. If I want to split it, what's is right here already, okay? So we import from sklearn the model selection, we're gonna import test train split, right? So usually if you write these train test split, and then you hit tab, come on, okay. Train test split, let me see. Okay. All right. Okay, so now I'm just gonna we import it, train test split. Now we're gonna do X train X test, Y train, Y test equal this. So is our train test split at our scale feature. And then our DF at target, DF at the target. Look, all of them are capital target class. And then test size here could be 20% or 30%. So test of lowercase, test size equal 30%, 0.30, for example. Right. So no problem. If you want, you can check the size of X test, Y test, X train, Y train. Right. So now let's use our KNN. Right. So our KNN, we need to import it from model selection. So from sklearn, from sklearn dot model selection. Oh. We want to import K neighborhood. To complete it. Neighborhood. So K neighbor classify, capital C, classify. K spelling, I want to make sure it's correct. K neighbor classify. Okay. So now, and then we can call sklearn the model selections. From sklearn that neighbors, we want to do that. K neighbor classifier, sklearn that neighbors, import K neighbors, there is S here, classifier. Okay. Now, neighbors. So because K can be more than one, right? So we can call our model KNN. So K near neighborhood is equal to this. In fact, let me copy this so that I don't forget any character. There is equal to that, right? And for K nearest neighborhood, you have to specify the number of neighbors, right? So that parameter is n underscore number of neighbors, yeah, right here. So for example, let's start with one, only one neighborhood. right? This is the model that we want to try first. And then that model, we want to feed it to our data, right? Our X train, Y train. So that fit X underscore train and then Y underscore train. Right, so we feed that. Now, we feed it. Now we need to do some predictions. So prediction is we're gonna run our model on the X test, right? So I will say pred equal our KNN because it learn from that training session. So we're gonna apply that to the X test, and that result should not be far away from our Y test. So how do we know that? X test. KNN. Oh, that predict. We need to predict it, right? That predict. And then that predict X test. Okay. What does it mean with neighbor? Only one neighborhood. You have a bunch of data set. You just want to divide them in one cluster, two cluster, three, so like that. You divide them in one class only. Obviously, this will not, right? This one neighborhood might not be a good idea, but we will see. We will see. Let's see. So we got one neighborhood only. Okay.
It's not based on any data view, like so US based on any suggestion why I choose one neighbor.
Yeah, usually if you visualize your data, you see there are like tenancy. Let's say you got tenancy, you got like 2, 3 classes, then you will choose the K to be 3, right? This one, I didn't visualize the data, I just randomly pick it. Obviously, I will change this. I will change this because it will not be the best value for our K.
Thank you. Mm-hmm.
So now, how do we know? How do we know that this thing is good? Yesterday we talked about it. How do we check the performance? Right. We use our metric. So from sklearn data metric, we want to import metric. We want to import our confusion matrix and then classification report, right? So import classification report, confusion matrix, right? And then we want to print them. So let's look at print confusion matrix at our, we're gonna apply that to our Y test and then our pred. So we misclassify 28 of them. We misclassify 17 plus 11. We misclassify those, right? Let's look at the. Oh, why I did this here? This is when I want to check with you. Check the value for K, because this K. Predictions. Let me do that here. Oh. I want to do it here. And this here too. This. Yeah. So now I want to print out the classifications. Print the classifications report. Classification report at our Y test. Y test, and we predict Y predict. Right. So it's not that bad, but we want to improve it. we're going to improve it by changing the value of K, right? So in machine learning, there is a method called K-fold cross-validation. It will let you know, that method lets you know how many K, what should be the value of K, right? The correct value of K. Did I erase that? So here, choosing the optimal value here. Yeah. So we want to do that using this method called, right, K-fold. So what we do, we start an empty list. That's an error. So our K and N, we start with I, and then I go from 1 to 40, right? This 40 is just a random. We can choose. I go from 1 to 50, 60. Usually, if K is too big, then right. When K is too big, the variance of your model will be smaller, but the bias will be smaller, but the bias will be higher, right? So you want to be careful with that. In other words, if K is too big, that model would be it will not be sensible, will not be useful for another data set. In other words, it will be overfitted for for the biggest value of K, you are overfitting it, right? If K is too small, then you are underfitting it also. So this method will let you know of the optimal value of K, right? So we are for looping it, right? For each value, from 1 up to 39, right? We wanna take our model, train it on the training sets, and then do the predictions on the X-test, and then append the result of the error. We're going to append it to this list. This is an empty list. And then once we get all of them, then we're going to plot, right? We're going to plot the error rates, from 1 to 40 again, right? And then these are just a color, you can change this color to whatever you want, right? And then these are the labels. So for this particular problem, let me see, looking at these, you can argue that 23 is the optimal. One can think that 16 also. These two values are close to each other. So it's your call, right? So once you get here, it goes up, but it comes back to the same level again, right? That means this is the elbow, right? So this is the elbow point, right? So you can choose K to be 23. I don't think it will be far away from 17 also, right? So when K equal 1, we get this, but when K equal 23, let's look at both of them. 1 is right here, right? But let's look at when K is 1, we misclassify 28 of them. When K is 23, we only misclassify 17 of them. And then the F1 score, look at the F1 score, has improved 94%. Right here, the F1 score was only 90%, 91%. So let's.
What about 17?
17?
Mm-hmm.
What 17?
Instead of 23K, if you use 17, because there's the starting.
Oh yeah. Let's do that. I can change it to 17 here. Let's see. That we also misclassify 17 of them, and almost the same results, right?
Yeah.
You see the F1 score are the same, right? The F1 scores are the same. Right. So look at here. So because of a cost, thing, I think I will choose 17 instead of 25, right? Here, this is more overfitting. here, this is moderately period. I'll choose this. Let me change that. What did I say? Optimal 17 is best. Right. So that's how you can improve the performance of your K nearest neighborhood. Okay. And you will have a project for these too, for this concept.
So that means they are organizing the data set into 17 cluster?
Yeah, yeah.
Mm.
Yeah, pretty much. K nearest, let me see if I can K nearest. Right. One is worse. Yeah, that's pretty much what he's doing. I believe in your project, the number of cluster I chose, I think it was a cancer data set. In your case, in your project, the number of clusters should be less than that even in the project that I gave you. Right. So again, I didn't talk about the mathematical behind these, the distance, the vector, the stuff. I didn't talk about it. But if you are interested, you can read the book called Introduction to Statistical Learning. That's an easy book to understand all these, the mathematics beyond this concept. Right. So the next thing that I want to mention is support vector mention. Right. So start from here. Support vector matching. So support vector matching is also another type of classification method, right? It will allow us to classify as to, the new data set belong to what class, right? You already have, based on the training data set, right? Then your models will be, classifying, the incoming data set, right? So, but the foundation of that is the following. So let's say you have these two data sets. Think about it, dogs and horses, right? So you want to be able to separate these, right? Horses with horses, dogs with dogs, right? So the question is, what is the best way? This line diagonal one is separate them. This one also separate them. This one also separate them. This one, you get many of them that separate them, right? So what line should we choose, right? Which one is better? You can have these, between these two, which one is better, right? Well, the support vector machine notion is you choose an hyperplane. So here, the middle. So you pick a hyperplane such that these two, the data set on the edge of the two classes, in this case, right, will be, the distance between them will be maximized. Right. So if you incline that data, that hyperplane, you will see that the distance will be smaller, the margin. For example, if you do it like this, let me go back like that, right? So the margin between the two edge point. By the way, the point on here at the edge, at the boundary, are called vectors. So that's what the word support vector machine come from. These on the support here, on the support of this hyperplane, they are called vectors. So that support vector machine come from these. Let me see. Just like the CI, yeah, like confidence interval. So you might say that we are increasing the variance also, right? Right, we are increasing the variance between these two. Okay. So in this case, our solid dash line is, our hyperplane, right? And then The vectors on the edges are called supervector, where the supervector machine coming from. Again, this is just in 2 dimensions. It could be in 3 dimensions, 4 dimensions, and then higher dimensions. Sometimes you go from 2 dimensions to 3 dimensions so that you will be able to separate them with a linear model, right? If you have a circle inside a circle, there is no way that you'll be able to separate them. But if you transform it to higher dimensions, then you will be easily be able to separate those 2 classes. Right? But I don't want to go too much in detail with the mathematical behind this again. So what I'm going to do, I want to do an example with Pythons. Right, so let me share my Jupyter notebook with you again. Start that. Support vector machine. Okay, super vector machine. So this data set that I'm using is already in scikit-learn. So what we need to do, we need to import the library first. Right, we'll use the cancer data from scikit-learn. Right. So easy. So I'll show you how to do it. So first, let's import the library. So let's come here and then create a new cell. We're gonna import pandas again as PD. Import NumPy as NP. Import. Do I need Seaborn? Yeah, I might use it. Seaborn as SNS. From matplotlib, or just say import matplotlib that pyplot as plt, and I want this in line matplotlib inline. So that's fine. Right. Okay, so now I'm getting data. So this is how you get it from scikit-learn. You will say from scikit-learn, right? From sklearn that data set. From scikit-learn that data set. Here, if you hit tab, it will complete it. We want to import load underscore breast cancer. I think it should auto complete it. Yeah. Load Boston is one of them. Breast cancer is one of them. That. Right. So that's built in scikit-learn already. So now the next thing that I want to do is to convert this to a Pana data frame. Right. So now I want to call this one cancer is equal to this. Copy it. So this load breast cancer data set. Now let's transform it to a Pana data frame. If you look at cancer, if you type cancer.keys, this is a dictionary, by the way. If you type cancer.keys with S, because there are morning keys, you will see it has data, it has target name, description, feature name, file, and so on, right? Okay, so if you want to have a description about this, if you want to have a description about it, yeah, and you can do the following: cancer, you do cancer this. Let me copy and put it here. It will give you some description about the data set. So now I know what's in there. I got the descriptions. Now the next thing I want to do, I want to grab the data. Right? If you want to know the feature name, you can do that too. In fact, let me show you the feature name. To get the feature name, you just grab the cancer again. Cancer at feature names. So like you see over there, it's a feature names, right? So you have a main radius, main texture, words, area, smoke. I don't know a lot about cancer cells, so I'm gonna skip this part. So now our data frame. So I'm gonna call it, let me create some anti-cell here. I wanna call our data frame DF feature, DF feature. So this feature will only consider everything except the targets. Target will not be part of it. So period that data frame, so we're gonna use a cancer because the dictionary, but we're gonna grab only the data. I don't know if you remember, there was a column called data. Let me double click this. Click this. This is where all our data is sitting. So I'm grabbing these, right? And then this is our targets. If I want the name of the data, feature names up here, right? Okay, so now that's what I'm doing here. So our feature is Panda of this. Now the columns names of columns is equal cancer at feature name. At feature name. So feature's name right here. Feature is a string that. Right. So now you can look at the info of the data, the feature, that info, that is, luckily there is no object, everything is a number, float, right? If you can look at the head also, you will see the feature names there. Right. Okay. So now I got the features. The next thing is the target, right? How do I get the target? How do I get the target here? Any suggestions? Target DF. I want target DF. We see here, the target is right here. Target name, and then the target is here also. To get my feature, I use a cancer on this. So, and then transform it to a data set, a data frame. Same thing for target, right? So target DF is equal to data frame for the target is PD, right? PD, the data frame, cancer evaluating IDs. Right, that would be my thing. And then the name will be, the name of the columns will be here. Cancer, we can just call it cancer instead of feature name. Let's do that here. Let's do that. So I'm not done yet. So I will say df underscore target is equal to, right, panda that data frame. So the data frame would take cancer at target. Targets is lowercase. And columns are just we call it cancer. That's it for simplicity. And we can look at the head of that thing. You will see that the name will be cancer targets. That head. That. So it's not only 0 zeros, right? Let me change it to 10, for example. You will see ones, right? So you get zeros and ones in target. So we got this data set from scikit-learn. We convert them to a panel data frame. Now it's time to split it into train. I don't want to do a visualization here because many of these don't make sense to me. I don't know much about cancer cells. smoothness, compactness. I will not be able to interpret it. But if you do, please feel free to do any visualization with MATLAB or Seaborn, pair plots, joint plots, right? But I don't know anything about this feature here. Okay, so now let's split it again, the same thing over and over again. We'll go from sklearn, that model selection, model underscore selections. Let me auto-complete it. We're going to import train test split, import train test split. Right. Now, same thing again, our X train, X test, Y train, Y test equal to our train test splits, right? Our train test split, our DF fit, the one that we did earlier, our DF features, right? And then here we need, if we don't convert these, let me show you this. Let me just call it the target here. Right. If I call just the target, DF target, you will see. So DF underscore, is that how I call it? Yeah, DF underscore target. If I just call that, and then what is this? Test size equal this 0.30, and then random state. If you want to have the same result like me, let's say 3 here. Right. So I'll split it like that. So this splitting, let me check the size here. Let me check the size. So let's say Y underscore train that shape. Let me see that. Okay, Y underscore test. So, okay, what about X test? So Y test. Okay, so that's fine. So now we have this. Now we can proceed. We can proceed with our. We can proceed with our model. Right. We split it. Now we can call our SVM. Let's call our SVM. So we can say from sklearn.svm, from sklearn.svm, SVM, VM. We want to import support vector classifier. Right, so that's the, we do it here, support vector classifier. Right here. Right. So we do that, and then we say our model is just equal to that. Our model is equal to SVC, support vector classifier, the insertion. Now we got our model. We need to train our model, right? So train the model. So our model that fits, we're gonna fit our X train and Y train. Okay. Okay, so there is an error here, say column vector Y was passed when 1D error was expected, right? So to avoid that, we need to do this, convert our Y here. Let me see, Y target. So we call numpy that. Let me see if this will take care of it. NumPy can do it. Okay. So now we find, let's predict it. So to predict it, we need to get our model now, because our model has been trained. We're gonna take it and then now run it on X test and then see if, so our model, because it has been trained now, we're gonna predict it. So that predict X test, X underscore test, right? And I'll call this one prediction. So prediction equal that. Prediction is equal our model that predict X test, no problem. So now we need to check. We need to check if model evaluations. So prediction and model evaluation. So we need to import our thing again, matrix, some sklearn metric import how do I call it? Classification report and confusion matrix. We're gonna import that and then we're gonna print each one of them. So our classification report at our Y test, so Y underscore test, and then Y underscore test, and then our prediction. So that, okay, that's not bad. That's our classification report. Now let's look at let me clear the kernel. This one is very good. I'm surprised. Let me clear the kernel and run all again. I am surprised we got these goods. Then if this is the result, there is no need for us to improve it. Okay, so let me see. This is good. This is good. And we start it. I just want to make sure there is nothing sticking in memory. Okay. Okay, this is good. But let me look at the confusion matrix. Right, so confusion matrix. Confusion matrix. So this is saying we misclassified 14 of them. Right, we misclassified 14 of them. Okay. 14 of them. So we can, we can make it better. Again, this is not that bad, but to make it better, right? To make your support vector machine better, there is a method called grid search, right? Because what we did, we just run the model with the default parameters. So inside the grid search, you can go ahead and then change the default parameters, right, to some, a list of parameters, right? Your parameter can take a list of values. So let's do that, right? In case in your projects you need it. So this is how you do it. So let's call the grid source. Let's call it param grids. Param grids underscore grid. So it's a dictionary. The key will be the actual parameters, right? So let me see my SVC. Let me see if I can print it here. SVC. Let me see this. Shift tab. If I look at my SVC shift tab, right now it has no more. Okay, so yeah, shift tab, SVC shift tab will let you do. So it has this parameter C, right? So if C is bigger, that means you got lowest bias, higher variance, and then you got another thing called gamma. I think it's gamma somewhere, parameter gamma. And verbose is set to false. We're gonna change it to some numbers because that will tell you, what your model is doing. If you set it false, you will not see. And then if you have to run your model for a long time, you might think that your model is not running when it is. So we can change that parameter C value. There is another parameter. There is a lot of parameters here that you can change. In fact, let me see. I think there is a gamma somewhere else that also deal with a variance and a bias gamma parameters. I probably pass it. Yeah, right here. This gamma parameter, we can also change that. Yeah, but feel free, you can change all of these. What we did, we just run the model, with the default parameters, with the default parameters. So what I'm going to do, I'm going to change those parameters now. Right, so for the C, right, the key is a parameter C, and then the value for the parameters, right, is a list. So I want to propose some values, so 0.1. After that, I'll do 1. After that, 10. After that, 100, 1,000. Right. I should stop there because my computer is not that powerful. And then the second key, gamma. Right, gamma, and then the value for that gamma also, I'll choose here 0.1. 0.01, 0.001, something like that. Let me stop at here, 0.0001. Yeah, that's it. Right, so grid search, once you change these, the SVC will go through each one of these parameters and then choose the best. Right, so that's what the word search means. So it will be going through one of these, you're gonna choose for the best parameters. Pretty much is searching. So I'll call this one param grid. Let me run it. So it's a dictionary, no problem. Now I need to import the grid search from the sklearn because this method is so important in such a way that it is scikit-learn has it built in. So we're gonna say from sklearn that model selection. We want to import grid. Let me see if I can autocomplete it. Grid search. Yeah, grid search CV. So capital G, capital S, capital CV. Right. So we import data. Right. So now we got it. We need to define a grid. Right. So I will say the grid. Our grid is equal to that. Let me copy because it's case sensitive. So is this grids are search that we just did, and then it will take in our super vector classifier model, right? And then I will introduce our best parameter now called param grids. Hopefully it's the same. And then the refits, see this, refit equal true. Refit equal true. Verbose, I'll just verbose, instead of false, because I want to see what the model is doing. I will choose that to verbose to 3, for example. That. Now, let me run that, no error. Now we fit it. So I will grid that fit X train, Y train. Okay, let me see here why this is error. Okay, no error. Okay, so if I didn't say verbose equal 3, I wouldn't be seeing these. This data is not that big. So if you're using a very heavy data, you probably might, run this code, go get some coffee, and then come back to see if it's done. Right. So be careful. SVM really, when you're using SVM, make sure the data is not that big. Right. This computation might take forever. Right. So now we have that. You can check the best parameters. Right. You can check the best parameters here. So grid the best parameters will let you know the best parameter for C was 10, and then the best gamma was 0.001. Let me change. It took my last one. Let me see if I can add another one, 0.00001. So instead of 3040, let me do that. See. So now I want to look at the best params. C went to 1000. Actually, that's not good. C is too high. So let me change this back. I took this. I want to change this. Actually, let me take it out. I want to take this because C was too big. In fact, 0.1102030. Yeah. Because you don't want, if C is too big, that means you got low bias, part of the variance is so high, right? Variance is so high. So this app, I'll rather use this than C equal 100 or 1000. So now we can use our grid. So grid, our grid that predict grid that predictions is equal grid that predict X test. Okay, so our X underscore test here, run that. Now we want to print our confusion matrix one more time, confusion matrix of our Y test, and then our predictions, right? So grade predictions, grade. So this here, we got only 11. We only classify 11, wrongly classify 11. Let me see before how many. So here it was 14, right? So it has improved it. Let me change this now, see what happened. And see 0.01. Right, so there is no fixed number that you should choose C to be, right? So here, let me see if that will improve it. Oh, that's worse. Let me look at that. That is even worse. So let me change back. Right, so there is no optimal number that this should be the value of C, right? So yeah, so that's pretty much it. 0. You can give any value that you want, parameter, range of parameters. and yes, see which one give you the best. So here, this is the best 11 misclassifications, and we got 160, true classifications, right? Okay, so to summarize, super vector, both super vector and k-nearest neighborhood, they need the data set to be, that's one thing that I didn't do here, to be normalized or standardized, right? And they don't do well on the big data sets, right? Unlike decision trees and random forests, they do well on, even logistic model also do better on big data set. But if your data is more than 100K, please do not use KNN or SVM unless you have a very, very powerful computer. Even that, the prediction might be, misleading. All right. Any questions? So, like I said, this, if you look at your SVC, there is a lot of parameter that you can change inside to make your model, right, to make your model more efficient. Right. So there is a lot of parameter here that you can go in and then change them. All right. Thanks, everybody. That's all I have for you. Williams, you there? You're welcome. So all the data set and Jupyter Notebook will be available for you guys. Thank you, Marietta. Thank you. Thank you, Jennifer. Thank you, Emmanuel. Thank you, sweetie. Thank you, Azad. Thank you, Azad. Okay. Denmark. All right. Yeah, Denmark, you looking for me? Okay.
Dr. Quasion, are you still on? Looks like he's still reconnecting to the audio. Can you give us one moment, everyone?